Well, hi everyone at home. Welcome back to Wednesday evenings from Cambridge University Astronomy. This is our penultimate Wednesday night. We have this one, and then we have next week, and then it's the end of the observing season. And not only that, this is the last observing we're going to be doing. It's getting very, very light, and next week it's going to be too light in the evenings to do any stargazing. And so this is our last stargazing evening. But I'm happy to announce that we do have some stargazing for our last stargazing evening. So after our speaker, we're going to be going across to the Cambridge Astronomical Association, who are going to see what they can see in the night sky. Before that, I'm very happy to introduce our headline speaker, Dr. Emma Curtis-Lake, who's going to be telling us how to build a galaxy. So over to you, Emma.
Thank you. So just to check, you see my slides?
I do. They look wonderful.
Okay. Thank you. So hello, everyone. Thank you for joining us. Tonight, I'm going to be telling you how to build a galaxy. This is something I do on a daily basis, pretty much, not the weekends. And I hope by the end of the talk, you'll understand why and kind of how I do this. So why are we building a galaxy? Astronomers can generally tell a lot about a galaxy from a series of images. So these are some really beautiful images of the antenna galaxies, which are a couple of galaxies that are merging. And we have here, these are a set of images from Hubble. It's a false color image. So when you take lots of images, so they're sort of stacked on top of each other with different colors for different images. The middle one here is from the Spitzer Space Telescope. That takes observations at much longer wavelengths and in the infrared. And over here we have something from the VLT, and that's much longer wavelengths still. I'm actually not going to talk about this one. I'm going to come back to these ones and concentrate on them. So the first thing we can see that comes out really clearly and nicely is that here we have this really dark patch. This is where dust is obscuring our view of the stars behind it. But this patch is quite bright in Spitzer. So Spitzer sees heat radiation. And this dust, although it's very cool, it's been warmed up enough by the stars that it's actually emitting light and looks very bright at longer wavelengths. So already we've sort of learned something from looking at these galaxies. But many astronomers don't get to look at such beautiful galaxies as that. So if we want to look at much further away galaxies, this tends to be what they look like. And I'm going to be referring to them as blobs throughout the rest of this talk. So these particular galaxies, because of the finite speed of light, it takes a very long time for light to reach us. So that means that the light was emitted from these galaxies when the universe was only a fifth of its current age. So we're looking back in time at the early universe. And because they're so far away, they're much smaller on the sky. We don't really see the details, and they're much fainter as well. And these are all images taken with Hubble. But even though we don't see so many details, we still might want to answer questions about them, like, are they forming stars? If so, like how rapidly? Do they have lots of dust, like the dust we saw in the antenna galaxies? And how many stars? If we were to weigh them, how heavy are they in stars? And we ask, what is their mass? And I'm going to take you through how to build a galaxy from some simple components that we will put together, the building blocks. So the first one is pretty obvious. Every galaxy needs stars. There are many different types of stars. We will call them different spectral types, and that will become clear why. So they're ranging from the biggest, brightest, hottest, shortest lived stars, these are the O-type stars, all the way through to the cooler, fainter, longer lived stars. And if you'd like to know what type our sun is, here it's a G-type star. But stars aren't generally formed in isolation. this is a picture of a very well-known open star cluster. It's the Pleiades. And you can pick out by eye in the night sky some very bright stars. There's actually many more stars associated with this cluster than you can see. And we actually believe that all of these stars were formed from the same molecular cloud. So when a cloud of gas collapsed and fragmented, it formed many different stars with an array of different masses. And this here, we call this a luminosity function. So if you were to count all of the stars and then categorize them according to their brightness, you can put them into different bins. But because we're astronomers, we often plot increasing brightness in this direction. So that's a bit counterintuitive. But what this means is we have many, many more of these low mass faint stars than we do of the high mass bright stars. And the ones that you're seeing, they're actually B-type stars in the Pleiades. So all of these stars look very different when you split up their light and look at their spectra. And these are spectra of the same types that I showed you in the slide before, 2 slides ago. And it's colored by the visible light, which is super nice. And where it's purple, this is looking into the ultraviolet. So our eyes can't see this wavelength, and that's why it's colored in purple. So these O-type stars, the hottest, brightest, shortest lived, they emit most of their light in the ultraviolet and at blue wavelengths, but they don't emit so much light at red wavelengths. Whereas as we go to the cooler stars, they emit more of their light at red wavelengths than at blue wavelengths. So you can imagine if we have a set of stellar spectra and we know what each type of star is in the Pleiades, that we might be able to attach a stellar spectrum to each of these stars. And by doing so, we've built a single star cluster. So this is the first constituent of our galaxy. However, a galaxy contains many, many, many different stars. You can think of them, a galaxy, as containing many star clusters. So after a while, after a long time, some of the stars will no longer be in the same place that they were when they were formed. So they may not be associated in a cluster of stars like we see here, but they would have still formed in a cluster. So we can think of our galaxy as being formed of many, many star clusters. But each of them is going to have a different age. It's going to be formed at a different time. So how can we'd like to do the same exercise of assigning a spectrum to each of our stars, but we need to know what type of star it is after a certain amount of time. And for this, I'm going to introduce you to a very famous diagram. It's called the Hertzsprung-Russell diagram. And in this diagram, if you order the stars according to their temperature, again, counterintuitive, so hotter in this direction, and according to their brightness in this direction, many stars make a really neat sequence when they're burning hydrogen. And we say that they live on the main sequence. But as time progresses, stars will start to evolve off the main sequence. And they do this when they run out of hydrogen in their core. So the first stars to come off were the hottest, brightest O-type stars. And I'm going to tell you about the evolution of the stars from this point here. At the moment, they're red supergiants. So in their red supergiant phase, they've used up the hydrogen in the core, but there's still a lot of hydrogen in the star. It's got a hydrogen burning shell and an extended envelope. So what's happened when it ran out of hydrogen, the core collapsed and heated up, and it heated up the outer envelope, and that allowed it to expand, and that's how it became a giant. But if the star is massive enough, it's gonna the core will keep collapsing, and as it collapses, it gets hotter and hotter, and if it gets hot enough, we ignite helium burning in the core. Then the question comes, what happens when helium in the core runs out? If it gets hot enough after more contraction, you get a carbon burning core, and then you've heated up the shell around it enough that you have helium burning in a shell around your carbon burning core, and you have hydrogen in a shell around the helium burning shell. And this continues. As long as your star is massive enough, this keeps going. So when the carbon runs out, the core will burn neon. When neon runs out, the core will burn oxygen. When oxygen runs out, the core will burn silicon. But when silicon runs out, we reach a supernova. So what's happened here? When silicon has finished fusing in the core, we're left with iron and nickel. So at each point when fusion has stopped, so hydrogen fusion stopped, the core starts contracting under gravitational pressure. But once fusion starts, energy is released, and that stops it from contracting. That's balancing. It's an outward force that's balancing the inward force. So as long as you've got something that can fuse and release energy, you're going to stop the contraction. However, elements heavier than iron, if they fuse, they no longer release energy. In fact, they require energy to be able to fuse. So that means that once you're left with iron and nickel in the core, it no longer will ignite fusion, and there's nothing to stop the collapse. And this at some point proceeds very rapidly. And depending on the mass of the star, you'll either end up with a neutron star, incredibly dense at the center, or even a black hole. So this is what we call a core collapse. That's not what caused the explosion. That's from the outer layers. So when the incredibly rapid collapse of the core happens, the outer layers, which do have elements that can still be fused and release energy, they're suddenly able to collapse very rapidly, heat up very rapidly, and there's so much energy released that the only way it can be released is through an explosion. So this is the evolution of the highest mass galaxies from the main sequence where they're burning hydrogen. But different stars of different masses will have a different evolution of the main sequence. And their endpoints will depend on how massive they are as to where they stop, at what element they stop their fusion reactions. But the point is that we actually understand a lot of this evolution. So if we were to look at the star cluster after a certain amount of time, the highest mass stars will have evolved off it. After a bit more time, some lower mass stars will have evolved off it, but we'll know roughly where they are in their evolutionary state. So this means that we have all these different star clusters and we have an age for them. And then we can say, okay, if this star cluster has a given age, here's roughly where it will be in its evolutionary state. And we know what each of these stars is doing. So we have a huge library of stellar spectra, and we have millions of stars observed in the galaxy, and then for parts of the evolution where we don't have observations, we have huge theoretical stellar spectral libraries. So we can assign a spectrum to every single one of those stars. And with that, we can construct the stellar component of our library, of our galaxy. So the next component I'm going to tell you about is the gas. This is a stellar nursery. It's where stars have recently formed. And like with the Pleiades, there'll be a range of masses of stars, but the hottest stars will be heating up the rest of the cloud that's left over, because when stars form, they don't use up all of that building block. There's still quite a lot of the cloud left, and that cloud is made up of gas and dust. And those hot stars are heating up the gas. And when the gas shines, it shines in a very particular way that we would like to be able to replicate. So a galaxy will contain many, many, many stellar nurseries. This is a spiral galaxy, and you can see there are some sort of bright patches here. And when we look at only the light that's being emitted by hydrogen gas, hot hydrogen gas, this is what it looks like. So these bright points here are stellar nurseries where the gas is being heated by young hot stars. And there are many of them, and they all have different properties. So the reason we can even take this image in the first place is because we know that different elements have a very specific fingerprint in how they emit light, and that's in their emission spectrum. So this is kind of the fingerprint for two elements that we expect to see in every galaxy spectrum. That's hydrogen and helium. And in fact, this line here is the one that was used to pick out that image of the hot hydrogen in the spiral galaxy. And this is the type of fingerprint that we'd like to add to the galaxy that we're building. But I'm going to remind you, this is a beautiful big spiral galaxy. Here's the wide array of many different stellar nurseries. And here are the blobs that I tend to look at. So we're going to make an approximation and not model each and every beautiful stellar nursery as a unique entity. But instead, I'm going to say, okay, most of the young stars, they're within their birth clouds. So we need to account for how they're heating up the gas around them. But the older stars, they're not. And then the properties of the gas, we'll give them average properties for all of the different individual nurseries. And then to be able to produce the individual spectra of these nurseries, we actually have to use quite a sophisticated code that sets up the physical structure of the cloud. You put a emitting source in the middle, and it works out the chemistry, it works out the physics, and gives you the fingerprints of the nebulae. So that's our star and our gas, in particular the hot gas. And the other component that I've already mentioned at the beginning of the talk is the dust. So if you remember, here we see a dark region where it's obscuring light from the stars. And if we look at longer wavelengths, we can see it emitting. So in the galaxy that I'm building, I'm only really caring about the optical to just about near infrared. The longer wavelengths, I'm not doing anything with, but other people do build galaxies where they also model the emission from the dust. To be able to tell what effect dust has on a galaxy, people have done a really clever thing. So we have surveys of millions of galaxies, and there's so many that you can take pairs of galaxies that are matched in as many properties as you can manage. So they're forming stars at the same rate, they've got the same stellar mass, they might even have as much the same chemical composition as you can manage. And the only difference is the amount of dust. And then you can imagine that by comparing those two galaxies, you can tell what is the leftover effect only of the dust on the light that's emitted. And what we see is that dust makes or obscures the light from the blue part of the spectrum more than it does from the red part of the spectrum. And it does this in a very smooth way. So I'm going to add dust, the same amount of dust to all of these stars. So gradually making this part fainter. But you'll see now, we didn't really make the red part of the spectrum that much fainter. So I'll just add dust once more, so you can see the blue part getting fainter. So that's kind of the general effect of dust. We can go one stage further, because we know that our stellar nurseries are made up of gas and dust. It's not only gas. So that means that the stars that are residing in those nurseries are probably seeing the effects of more dust than older stars that are not still within their nurseries. So we'll attenuate the younger stars more, or give more dust to those younger stars than we will to the older stars. But it's still quite a simple model of a galaxy. So at this point, we've got our three main constituents. And then you might like to have some fun and add something more exotic, the cherry on the top. And the one thing that we can add with the program that I use are accreting black holes at the center of the galaxy. So we can add the effects of gas that's been heated by basically a central black hole. But this is really just the cherry on the top, and you need the other constituents, but you don't always need this one. So putting all of this together, what can we do by building galaxies? So this is a simulated image. None of these galaxies are real. And we made this using Beagle. So this is the program that I use to build galaxies every day. And the reason we wanted to build this image, and in fact it's a catalogue of sources, is so that we could mock our universe, because we wanted to test survey strategies for an up-and-coming space telescope that we hope will be launched later this year. And this telescope is going to be observing galaxies that we cannot see with Hubble. So if we want to know if we can detect them, we have to simulate them. We have to make them from scratch. So this is an example spectrum of one of these galaxies we built. And so this is showing it in a different way, but these spikes are the fingerprint of the different elements. So this one here is from hydrogen. Here we have a couple from oxygen. So dependent on what elements are in the birth clouds that are being heated up by young stars will depend on the pattern that we see in these emission lines. And then the rest is the stellar light, and it's been all added together for this galaxy because it's really just a blob and we don't see much detail. And then we've also added dust to it. And then these profiles here, these are actually the bits of the spectrum that are picked off with different images with JWST. So the last image I showed you uses this filter, and this filter to make it. So it was a false color image written here. If an object looks red, like this one here, it means that it was only really picked up in this filter. So how an object looks throughout the different images will very much depend on how it's sampling the spectrum. And that's what these points show. So this particular galaxy would look much brighter in this hard to see filter here than it would in this F200W, which is the red filter from the previous image. So these are made up galaxies. None of them are real, but they're very helpful. But we can also build galaxies to help us learn about properties of real galaxies that we do see. So to do this, we have observations, which are each of these blue points. They are how bright a galaxy is in different images taken with Hubble. And then Beagle builds thousands of different galaxies and compares them to these to see if any of them look similar. And so the red region are the ones that look similar enough. So they're actually quite wide regions because we couldn't figure out too much about this galaxy. And then because we know the properties of those galaxies that we build, we can learn something about the observations of this galaxy. So the next plot I'm going to show is very busy, and I'm just going to pick out a couple of things to point out. I love looking at these plots because I look at them every single day, but I'm not going to explain to you fully what it means. But each of these is a different parameter that we're trying to learn about in the galaxy. And when it's dark blue, it means that it thinks it's at that value. So this one is stellar mass. So this galaxy, Beagle can't tell whether it's very massive or not so massive. It's got 2 peaks in its probability. But this is dust. And what it seems to be showing is that Beagle thinks that there's quite a lot of dust. So dust increases in this direction. And we might even be able to guess this just from looking at this SED and knowing what I told you earlier, which was that dust makes attenuates light in the blue wavelengths much more than it does in the red wavelengths. So just looking at something that looks like this, we might guess that there's quite a lot of dust in it. So by building these galaxies from simple components, we can simulate fake galaxies to help us prepare for up and coming space telescopes, but we can also learn about current galaxies. And with that, I'll finish and I can take any questions.
Wonderful. Thank you so much, Emma. That was absolutely fantastic. It's lovely to hear about the actual like nuts and bolts that go on in the work that we astronomers do. So I can see you guys obviously know the deal by now. The questions are coming in thick and fast on the YouTube chat. Anyone that hasn't asked a question yet but wants to, the YouTube chat is down there in the corner. I'm going to start off with this question from Elena. So she wants to know, if you use different wavelengths, is there a chance that a telescope is going to miss something that another telescope might not miss?
Oh, yes. There's a really nice example of this. Let me see if I can, I've just stopped sharing the screens. Let's see if I can go back. This is a nice example. These are Hubble filters, and this particular galaxy, because it's so far away, we actually can't see light beyond this point. So if we were to push this galaxy a little bit further away, everything gets shifted in this direction and we wouldn't see light in Hubble at all. So we wouldn't be able to see this galaxy at all in Hubble, and we could only pick it up in JWST. So that's one example. There are many other ones that I could go through, but this is quite a nice one because I have a slide.
Okay, so we have a question from Linda Bostock family. As I always imagine they're watching as a group. Well, first of all, they say it's a daft question. It's absolutely not a daft question. It's a very sensible question. They want to know, how are these stars burning once all their oxygen is used up? Because, you know, we learn in school that everything needs oxygen to burn.
Oh, what a great question. So when we say burning in the context of stars, we're meaning something very different, and it's something that we can't create in a laboratory because it would give off too much energy and kill us, probably. So if you take 2 hydrogen atoms and push them together enough, they will make a helium atom, and this is called fusion. But we didn't need any oxygen there at all. But we would still call that burning hydrogen. So it's a different process from when we're burning things like making fire in the laboratory or in your kitchen or anywhere else.
Okay, a nice and easy one for you. How many galaxies are there in the universe?
Oh no. Well, okay. We can't count them.
For people watching at home, I was joking. It is not an easy question.
Yeah, I'm not sure if the technical answers to that would be it could be infinite because there is no edge to the universe. However, there is a finite number that we'd ever be able to see. And if I were to go into that, this would become very complicated and I would definitely explain it wrong. But take as many zeros as you can put behind that one as you can and keep going. And that's probably getting there.
So we've had a couple of people asking about the role of black holes in these simulations. One from Jim, who asks, at what point in the galaxy modeling process do you put the supermassive black hole in the center? Is that part of these simulations?
Yeah, so we're looking very much at certain things that we can observe. So there's different things that you see with a black hole depending on how you look at it. And there's a region of it where we have some gas that it's not obvious unless you're very careful that it's heated by a black hole or from star formation. And that's what we're most interested in adding to our models, because there's sometimes what you see is very obvious that it's got to come from a black hole. We're more interested in the edge cases, and we add it on top of everything else. So we've got all our stars, dust and everything else. And then this particular region, which is heated by the accretion disk, we add kind of on top, but it's still within the galaxy in the sense that it still sees dust. But
okay, so I guess following on from that, someone has asked, is there a more precise definition of dust? I mean, what do we mean when we talk about dust in space?
Yeah, okay. So it's generally sort of quite large particles of hydrocarbons and heavier elements. So anything that's sort of bigger than a molecule can start to contribute and be called dust. And they range in size beyond that. So they can be as big a clumps as you kind of want. But yeah.
And a couple of people are also asking, notice that you didn't mention dark matter at all when we talk about how to build galaxies. Is there a reason for that?
Good point. Well, the reason is that when we're looking at light from images, we don't need to input the dark matter to be able to interpret it. There are times when you might want to input the dark matter because of its effect on certain objects, but for the observations that we're looking at, it has no effect on what we're seeing.
Okay, a question from Shem that I think you're very well positioned to answer. Will the James Webb Space Telescope be helpful in learning about these distant galaxies?
Oh yes, we're just waiting for it because it feels like we've learned what we can, and that's not quite true. So there are two particular things that James Webb gives us. One is here's where Hubble ends, and here's where James Webb begins. So for the very, very distant universe, Hubble was only telling us about a very small fraction of this galaxy. JWST is going to tell us about all of the rest of that, and also give us spectra. So we'll be able to look at what elements are present in the galaxies. So yeah, it's going to be transformational, I think is the word that we tend to use.
Absolutely. I think pretty much everyone in the astronomy world is very much looking forward to James Webb going up. I think that we're probably going to leave it. I can see there are a few more questions, but I know our observers are probably waiting, shivering in their telescopes, ready to go live. So Dr. Emma Curtis-Lake, thank you so much for that absolutely fascinating talk. Before we go over to the Cambridge Astronomical Association, I do want to quickly plug something coming up next week, which is the Cambridge Festival. So the Cambridge Festival is an annual thing where all the departments in the University of Cambridge put on this whole wonderful array of activities and talks and various things for you. And here in astronomy, we have various crafting activities for children and talks and other wonderful things. And it's all going to be happening right here on our YouTube channel. So if that sounds interesting to you, give us a subscribe and check us out next week. You'll see all the things we're doing. We have a series of talks all about the black hole information paradox. We are learning to bake galaxy cakes, and we are finding out what physics you can do in your kitchen. So we have all kinds of things on our channel starting from next week. Cambridge Astronomical Association, guys, how are things looking in your telescopes?
Well, it's quite clear where I am here to the east of Cambridge, west of Cambridge, but looking east, I've got a bit of a problem. So I'm going to have to keep Brian, our commentator, on his toes, because none of the objects he's given me to look at are without cloud at the moment. But I'll show you what I have got, and this will all be very familiar to Brian, so it's not going to frighten him at all.
You bet.
I'm cruel to you. Do you know what that is?
Sorry?
Yes.
Do you know what that is?
No.
Hang on.
It's the trapezium in the center of Orion.
All right.
Oh, goodness.
Yeah, and we can zoom in a bit, and you can see the 4 stars twinkling away there.
Yes.
Over in the west.
Right.
One slightly fainter than the other, and you can talk about that, Brian, and then I can give you the nebula if you want.
Yeah, okay then. Right, when Galileo first looked at this region of the sky, his telescope wasn't very good, and he could only see 3 of the 4 stars. But he didn't see the nebula. And these are bright young stars, and they've hollowed out the gas cloud, and from this gas cloud other stars have formed, and there's a whole cluster of stars, of young stars, near the trapezium. The trapezium are just the brightest stars, and especially that big blue one at the bottom, that is the one that has caused most of the hollowing out of the gas cloud, so we can see inside it. And this giant molecular cloud can be it covers most of the bottom region of the constellation of Orion. Okay, Paul, do you want to crank it up so we can see what happens to the nebula?
Okay, so I'm doing a 10-second exposure for you with my DSLR camera, and here it should be coming up now. Where's it gone? It's hiding in the window at the back, isn't it?
Here we come. Yeah, we can see it. Of course, Galileo's telescope wasn't good enough to show any nebulosity, but even with a pair of binoculars, and you look at this region, although with binoculars it will be on a much smaller scale than Paul's telescope, you can still see it, but you won't see it in colour, because our eyes are just not as sensitive as the cameras that we use. So this is the advantage of using cameras. We get the colour, and this is of course the hydrogen that is being excited by that big blue young star that we can see at the bottom of the trapezium. The other 2 do contribute a little, or the other 3 do contribute a little, but it's mostly that big star that has blown out this gas cloud, this cavity that we're looking into. And the whole gas cloud is about 20 light years across the cavity we're looking into. So 20 light year cavern, if you like.
Sorry about that. I'm having a little fun and games with the image here.
No, that's okay.
That's not one of mine.
That's not one of yours. Yeah,
that's what it should look like.
Yeah, but we're struggling with the moon. We've got a nearly full moon that is lighting up part of the sky, and if Paul makes the camera too sensitive, all we'll do is we'll lose the image, because the sky will just go bright. So
Yeah,
you,
it was better than this just a few minutes ago. So I
So
think we've
we're-
got a bit of cloud in front of the target at the moment.
okay.
In fact, yes, I can't actually see Orion's belt with the naked.
Right. Okay, so we'll pop over to David and see what you've got.
Hello.
Hiya.
If you come off, Paul, I can share.
Over to you, David.
Thank you. There we go. This is NGC 4565.
Yep.
We're
can
actually
see.
looking at it through the top branches of my neighbour's tree.
Right. Right. This is can you enlarge it a bit, please?
Yes.
This is a galaxy. What we were looking at before was a molecular cloud in our own galaxy. Now we're looking at another galaxy further away. And this galaxy is also called the Needle Galaxy because it's very thin. And it's seen edge on. A galaxy is like two fried eggs back to back. And that's brilliant.
There you are. This isn't live.
There's some cheating going on here.
There's a meeting going on here. Paul
Yeah.
can do this. I can do this.
Yeah, but you might as well leave that one on. I'll just say about the dust lane that we can see. If you can pop it back, please.
Yes, if I can.
There we go. Oh.
Windows decided you don't want to look at that. Hang on. Let me minimize this.
Right. Well,
there we are.
That's better. Okay. But what we can see about the Needle Galaxy is there's a band of dust going right along it. We're seeing the spiral arms edge on, but that dark band is the dust and gas within the spiral arms. And despite this gas and dust blocking our view of the central bulge, we can see that the bulge is quite bright. And this is a Seafoot galaxy. Now, this was a group of galaxies noticed by Carl Seafoot in the 1940s that they had a very bright nucleus. And these galaxies are known to have active nuclei. And that's where a disk of material is spiraling around and falling into the supermassive black hole at the center of this galaxy. And it's the black hole is feeding. That's why it's giving off it's so much radiation and the nucleus is so bright. Unlike the Milky Way, which is feeding it, our supermassive black hole has been on something of a starvation diet for the last few million years. Although detections of the odd dainty morsel falling into our black hole have been spotted. And these snacks are nothing much bigger than something the size of an asteroid going in. But when more material falls in several solar masses, that's when the active, the nucleus becomes really active. And we can see that the Needle galaxy is very thin, and it's some of the other galaxies, well, one of the other galaxies we were going to look at, but Paul's having trouble with cloud, was quite chunky. It was quite fat. But astronomers reckon that our galaxy is one of these thin edge-on ones when you look at it edge on, it's quite thin. So that's NGC 4565.
Okay.
Okie doke. Shall we go on to Mick now? Have you got Castor? Mick, you're on mute.
There we go.
That's it.
I'm just going to have to adjust it because I'm getting a bit of cloud.
All right, we'll do the best we can.
Oh, I've lost.
Is this Castor that's going to be?
Yes, it's just there. Hang on.
Right, we'll wait. Well, while he's getting it,
There we go.
there we go.
See it?
Oh, you're on the moon.
Yeah.
Okay. Yeah. Sorry, I thought you were on Castor.
I'm,
No, I can see it's definitely the moon now. Right, and we can see the cloud going across the moon, and it's getting better all the time. Now it's overexposed, but Mick will adjust that. We're currently at the Sea of Crises, where the arrow is, the dark patch. That was where we left last week. We looked at the Sea of Crises, just there where the arrow is. And we looked at an object called O'Neill's Bridge, which was just purely an optical illusion that, just where Mick's pointing, an optical illusion that makes it look as though there was a natural bridge there. But now, that was when the sun was just rising. But now the sun is almost directly overhead. And we can't see any detail because there are no shadows. However, this, while the sun is overhead, it shows the ejector, that stuff that has sprayed out of an impact. And we're looking at the bright crater in the middle called Proclass. And Proclass is a young crater. We're getting some more cloud, and it's young because the ejector, the stuff that's splashed out during the impact, is still quite bright. By young, I mean just under 100 million years to a crater on the moon. That is young. So the ejector will gradually darken over hundreds of millions of years, but we can see that it's not even, it's fan-shaped. And it means the asteroid came in at a very low angle from about 7 o'clock. So, and the material has been splashed out through just over 180 degrees. Here we can see it. You can see there's no debris being thrown out between 11 o'clock and 4 o'clock. All the other debris is round the other side of the crater. So that's an unusual impact because, as I say, it came in at about 15 degrees to the surface of the moon, which is quite a low angle, but the crater itself is still round. Generally, you find no matter what angle the crater is at, it will always be round. Now, if we go down to the Sea of Fertility, so if we leave the Sea of Crises and go down to the Sea of Fertility, and we're looking for another crater, or it's actually two craters, called Messier. Now, you've heard us call objects Messier or M objects, and these are named after the French comet hunter who made a list of fuzzy objects that shouldn't be mistaken for galaxies, but it's what we tend to look at. Right, we can start to see, we just need this cloud to go. We can see that there are two craters. You're doing well with the cloud, because for people who don't know, when the cloud goes across, it alters the exposure of the moon, and poor Mick has to frantically try and adjust it to get an image. But we can see those two blobs, and those craters are called Messier, the one on the right, and Messier A on the left. And what's happened is that a half-kilometre asteroid has come in from the right-hand side at an extremely low angle, probably just 3 degrees above the surface. And it struck the moon where Messier A is. We'll just see if the cloud will shift. No, it's getting worse. Here it comes. Yeah, can you point to Messier A? That's it. And it hit at such a low angle, it made an oval crater. It's 9 kilometers by 11 kilometers. And then it bounced 20 kilometers and made the second crater. And you can see the ejector only goes to the right, left-hand side. So this is incredibly unusual for an asteroid to hit the moon at this sort of angle. So it was just basically skimming above the surface when it hit the moon. And so you've got two craters roughly 10 kilometers in diameter. And this is how you work out the size of the asteroid. You divide the size of the crater by 20. So obviously if you've got a crater 20 kilometers across, it means an asteroid 1 kilometer hit it. Okay, shall we whiz down to Tycho, please?
Yeah, just give us a sec. Right.
Okay, and these seas that you see, the dark areas on the moon that you can see with the naked eye, are just huge impact basins that occurred long, long ago. But we can see some stripes on the moon all seem to be pointing towards a crater. We'll come across that crater. The stripes on the moon is the ejector coming out from this crater here, which Mick will point to.
This one.
That one, yay. That one, that's Tycho. And another young crater, but much bigger than Proclass. And it's about the same age as Proclass, just maybe a little bit older. So both these craters that we've shown you were formed as the when the dinosaurs were clumping around on the Earth. Now, if you can get, can you take Tycho down to the bottom a bit so we can see if we can see the ray system, the stuff that splashed out? Yes, we can. You can see pathways of light.
There we go. You can see that.
Yeah, you get some of it goes to the going up to the top corner, and some going off in all directions. And when the moon is full, if you look at the moon with a pair of binoculars, you can see this ray system or ejector pattern spreads right round the side of the moon that's facing you. And you can follow it right round the moon. So this is, again, because it's a young crater, we can see these the stuff that's come out of the crater. Now, if we go down a bit, we should come to the largest crater on the moon. And there it is. It's It's called Clavius, and it's about 230 kilometers across, and it's very old. It's about 4 billion years old, sort of similar age to some of the impact basins or seas we see on the moon. And despite its enormous age, it's quite well prepared, quite well preserved. It's not too badly eroded. And the thing I like about Clavius is that it's got 5 craters on its floor, getting smaller in an arc. Can you point them out? So you've got an arc of 5 craters on the floor of Clavius, getting smaller. And this is obviously, as I say, a very old crater. And then we come to the another crater just to the left of Clavius. Keep going. Keep going. It's that oval one.
Huh?
That one. That's it. Now, I know we're near the edge of the moon and all the craters appear oval, but that's just purely the foreshortening effect. But that crater that Mick was pointing to is called Schiller, but it really is oval. And it's sort of 180 kilometers long, but only 70 kilometers wide. Now, it's not made up of separate impacts, and it wasn't formed when an asteroid came in at a low angle, because it's too oval. What they think happened is that an asteroid came in to hit the moon, but broke up into 3 or 4 pieces. And the 3 or 4 pieces hit the moon together. And while the surface of the moon was liquefied, it behaves like a liquid during an impact. It sort of blended into this huge oval crater. So that's called Schiller. And this whole area of the moon is very heavily cratered, as you can see. There's craters on top of craters. And this is how you date craters. You just keep an eye on them. You can see which ones are overlapping the others. So obviously younger ones overlap older ones. And some are so badly eroded you can hardly see them at all. There's one up near the sea there where you had your arrow, which is almost filled up. If you go back to the right at the bottom of the next small patch of sea, if you take your cursor.
Oh, sorry.
Yeah. Keep going to the right a bit. Keep going. Keep going. Now go down. Down, 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 down. Stop. That's it. That crater is almost a ghost crater. It's got the southern rim is quite pronounced, but the northern part of the crater is more or less disappeared. And some of these ghost craters are even more harder to see than this one. Now, in approximately 4 minutes, there's going to be a satellite going across the moon. And our 3 observers are all going to point their telescopes at the moon and try and capture this satellite going across the moon. This doesn't happen very often, and we're going to keep our fingers crossed. We've never done this before, so what we'll do is we'll stay with Mick. And
actually, Brian, can I just I've just found you a galaxy. It's just to show you how terribly close to the moon these things are.
Yeah, we
and
got a
then when
few
I've done
minutes.
that, I'll slew over to the moon. So can I just show you that in the 2
Yep.
minutes?
Yeah, we got.
And then I'll slew to the moon.
Yep.
So if Mick stops sharing, I can do that.
Right, this satellite that I'm talking about is called Cosmos 724, but we'll come to that in a few minutes. But we really are battling the moon. No, I can't see a
There's your
sausage.
galaxy. Can you see it?
No, I can't.
Unfortunately. Oh, come on, it's there. Right by the point of the arrow.
Yeah. So you can see
That's
that
what I'm battling against at the moment. But as soon as you moved away from me, I got that. Because the cloud shifted out of the way. And earlier I got a really nice shot of the moon. So I'll go over to the moon now because the galaxies are just not going to work for us tonight.
Okay. Right. If you stick with that picture or go to the moon, you've got a couple of minutes. And this
so if someone else wants to take over while I slew, I'm just going to use my star map.
Well, we need to get the moon.
I'm going to the moon.
Who's going to show us the moon? Mick, are you ready?
I can't if I can find. Hang on.
Right. This satellite. You probably heard on the news that on Monday that there was a launch and going to be a test of the astroscale debris removal spacecraft. There are about half a million pieces of space junk up there, and they're becoming a bit of a nuisance. And one of these bits is this dead Russian Cosmos spy satellite launched way back in 1975. And what we're going to do is orbiting the Earth at about 900 kilometers. You've only got a minute, Mick. You need to get your skates on.
Do you want me to share?
Share, go, go for it.
My camera battery's just run out.
Right, that's it. Okay, where are you going to find the asteroid? I mean, the comet. You need to go up a bit. Go up a bit, and because it will go right across the middle of the moon. So you don't want to be. Keep going a bit. Keep going. Keep going. Keep going. Right, keep going. Now go to the right a bit. Sorry, the other way, the other right.
I'm having to control it with a laptop at the same time.
Okay, now go down a bit. Whoa, go down a bit. So we got a bit of black sky. There we go. That's all right. Whoa. Right, we should, in a few seconds, see this satellite streak across. And if it doesn't work, well, we tried.
Right, I'm on the moon now with a working camera.
Yeah. Are you recording, Paul?
I'm going to try.
Yes, I'm recording.
Because it's...
When's it supposed to happen?
It's supposed to have happened. It's gone. So we didn't see it on Mick's telescope.
No, me neither.
No. Oh, well, it was worth a try. It's just they said it was it's a ocean surveillance spacecraft. And I don't think it was used for studying the waves and ocean currents, because they put 100 others up just like it. I think it was, my guess is it was for keeping an eye on certain ships from America and other countries. But anyway, we can see right in the center of the crater, there's a crater, nice crater in the middle there called Plato that has filled up with lava. Okay, I'll just see if David did manage to record it.
No, I'm afraid not.
Oh well, three failures. Never mind, it was worth a try.
And I'm sorry to report I've got the same galaxy problem as Paul.
Right.
I can see stars, but nothing behind.
We'll stick with the moon. So we'll go to Paul for the last couple of minutes to look at the moon before we have to wrap up.
Okay.
Okay, ready when you are.
Yep, here we go. So I've zoomed right in on the crater Plato for you.
Yes, we can see. That's very nice.
Talking about it, it's rather nice, that, isn't it?
Yeah, and we can see a slight bit of turbulence caused by the atmosphere, but actually the atmosphere is very, very steady tonight. Usually when we look at the moon, it's wobbling about like a jelly, but this is remarkably steady. We can just see a slight bit of blurring. And this is, of course, why all major optical telescopes now are built high on mountaintops to get above the thickest part of the atmosphere and the horrible blurring effects that causes this. And what we can see is there's a rift valley to the right of Plato, where two parallel faults have formed, and then the ground has sunk between them, and you've got that light band of material that's the sunken ground between the two faults. If you can point that out, please, Paul.
It's just from here, where this little dark shadow is, all the way along through here.
Yeah, that's
looks like a railway cutting.
Yes, it does. It's much better when the sun isn't quite so high and we get more relief. So if you want to troll over to Aristarchus.
Okay, what I can do is I think Aristarchus might be on the unlit side.
Oh,
over here, look.
Yeah.
So this is Copernicus. And
probably
and then we've got the Terminator. So
go with Kepler, or you go with this Bay of Rainbows.
You want me to go to the Bay of Rainbows?
Yeah, we start.
That's this bit here.
Yeah.
And what I can do is deploy my super zoom. Come on, where are you? There we are. And then I've got to drive it around, so it's this way. Over to the edge and down a bit.
Now at the Terminator, we can see that there's much more relief, and we've got shadows, and things start to make sense. We get the depth of field of view, and here we are with the Bay of Rainbows. This is a huge crater that's filled with lava from the sea, from the ocean of storms that it's on the edge of. And then you might as well work down the Terminator so we can see what we can see as we just finish up. We've got a couple more minutes before we have to finish. But I don't think you're plagued by cloud quite so much as...
No, it's gone now.
Yeah.
Inevitably. You've got some nice wrinkle ridges here, look.
Yes.
Folds in the ground.
That's where the lava has cooled, and it's wrinkled as it cooled.
A crater rim just catching the sunlight.
Yeah. That's not far from Aristarchus.
It's not far from it, no.
No.
Just that's a little bit further over.
Yeah.
It's,
and then we might as well go over to Copernicus, which is a lovely crater, another youngish crater.
That's this one here.
Yeah.
On the main screen, I'll drive the zoom over there.
And that again is very prominent in binoculars.
There it is.
Here we come. We're getting some shadow, so we can see. It gives us a good depth of field of view, so we can see its sort of relief. And this crater is about 50 miles or 80 kilometers, and it was it's understood to be formed from an asteroid called Eulalia, which was considerably bigger and broke up about 800 million years ago. And as a result, the Earth and Moon were heavily bombarded by bits of these asteroid. And from a study last year, from the data from a Japanese lunar orbiter called Kaguya, showed that of a survey of nearly 60 craters, 8 of them were formed at the same time as Copernicus. So it shows that the moon really did get clobbered by this asteroid that broke up 800 million years ago, or about thereabouts. And samples taken, because the ejector carries on going downwards, and not too far below the Copernicus crater was where the Apollo 11, the Apollo 12 astronauts landed, and they took samples from
here, wasn't it?
It was down a bit further.
Was
just
it?
Yeah,
below this one.
Below that one, just keep going down. Nearly there, but you can see some of the. That's it. It's about not too far from where you are now. So that was the Apollo 12 landing site where Charles Conrad and Alan Bean landed. And it was Bean noticed that Conrad's footprints showed lighter material underneath. So that proved that the ejector from Copernicus was covering the landing site. And so they took some of these samples and they dated it to 810 million years. So that sort of ties in nicely with the story of Eulalia breaking up. Right. I think we've just about run out of time. Anywhere else you want to look at, Paul, before we finish off? Shall we have a look at Kepler?
Yeah, okay. I'll take you over to Kepler. He's just this way, isn't it?
Yeah.
Brian?
Yeah.
I do have your second galaxy.
You do?
I do.
Shall we go for it?
Right, I'll give way to David if you've got something other than the moon.
I believe I have it. I know Brian will recognize it.
Thank you.
Go here. Here. Can you see?
Can you enlarge it any?
I can enlarge it, and
because the trouble with Zoom is you do tend to lose a little bit of resolution. So while you might be able to see it, we're struggling a bit. Oh yes, I can see it.
Something.
Yeah, we can see.
Yes.
Yeah. Now this is a monster galaxy. I know it doesn't look very impressive, but it's in the constellation of Coma Berenices that follows behind Leo. And this is a giant elliptical galaxy. Up till now, over the season, we've only ever looked at spiral galaxies. But this is a giant elliptical galaxy, and it's at the center of the Coma cluster of galaxies, which is about 2,000 galaxies. But despite the fact it's not looking very impressive, it's because it's so far away. All the galaxies we ever look at are probably 20, 30 million light years away, whereas this is 300 million light years away. and is very distant and appears very small. But it's a monster, and it's about 10 times the diameter and 10 times the mass of our own galaxy. We can just see it as this faint little blob. So you'll just have to use your imagination that this is a humongous galaxy. And you tend to find elliptical galaxies at the center of clusters of galaxies, and they just get big by eating other galaxies. Because don't forget, when stars are an enormous distance apart compared to their diameters, where galaxies are often only just a few diameters apart. And so galaxy encounters are quite common. And that's why you tend to get these giant elliptical galaxies at the center. They've just munched on other galaxies. And of course, it's got a supermassive black hole at the center because of all the stuff it's eaten. And this black hole at the center of this is about 5,000 times bigger than the black hole at the center of our galaxy. And that makes that one of the largest black holes known.
I don't know if you can see, Brian, but there are actually many galaxies on this.
Yes, we can. I can see a second one quite easily. And
if I do that, there's here.
We can see the main galaxy.
Here.
And some of them are quite close, so it will feed on more galaxies. So we're right at the heart of the Coma cluster of galaxies. So as I mentioned, it's got about a couple of thousand galaxies in this huge cluster of galaxies. And this black hole isn't eating. It's a bit like our the Milky Way's black hole. The Milky Way hasn't had a decent meal for millions of years. And this supermassive black hole, this giant black hole, isn't eating either. But during its heyday, when it was swallowing up many solar masses of material, that giant elliptical galaxy would have been classed as a quasar. And that's where we'll finish for tonight. And thanks very much. And I'll just thank our telescope crews, Mick, David, and Paul, for battling the battling the clouds, and we got there in the end. Thanks very much, guys, and we'll hand you back to Matt.
Cool, and thank you very much, Brian. And yeah, like you said, to all of you at the Cambridge Astronomical Association, it's been a very strange year, but I really appreciate that we've been able to do these things online. It's been really awesome to take our traditional Wednesday evenings into YouTube. So this is not the final one. We have one more of these next week, this Science Festival edition of our Wednesday evenings with Dr. Gareth Jones, who's going to be talking about the distant and dusty universe, along with a whole range of activities that week. And then that'll be it. And then we'll see you in October. But before that, yes, we'll see you next week.